Greetings, everyone. Welcome to today's webinar. I'm Jonathan Wiener, the co-director of the Duke Center on Risk. My co-director, Mark Borsick, and I started the Duke Center on Risk a couple of years ago, and we are delighted to offer you today's webinar in our series on perspectives on planetary risks. And today's topic is COVID-19 transmission, estimating risk in indoor settings. And we are delighted to have with us today two experts on that question of estimating the risk of COVID-19 or SARS-CoV-2 transmission in indoor settings. We'll have two speakers followed by question and answer discussion. And before I introduce our speakers, let me say that many of you submitted questions in advance as you registered for today's webinar, and we very much appreciate that. And I will try to call on people who submitted those questions to pose your questions orally during the Q&A period. In addition, for those who would like to pose a question during the session today, you can use the Q&A feature at the bottom of your Zoom screen to pose an additional question, and we will try to keep track of that. And I'm glad to be assisted today by our research scientist, Dr. Tyler Felgenhauer, and by Tim McDermott of the Duke's Initiative on Science and Society. And Tyler and Tim may help us keep track of the Q&A. So thank you all again for joining today's webinar from the Duke Center on Risk in Science and Society on the subject of COVID-19 transmission, estimating risk in indoor settings. Our first speaker, and I'll introduce both speakers now. Our first speaker will be Dr. Jose Jimenez from the University of Colorado at Boulder, where he's a professor of chemistry and a fellow of CERES, and one of the world's experts on aerosol transmission. He holds a PhD in mechanical engineering from MIT, and his research has focused on advanced real-time aerosol measurements and their application to settings such as aircraft, laboratory studies, and also on mathematical modeling. Jose is a fellow of the American Association for Aerosol Research and the American Geophysical Union. And after Jose speaks, we will hear from Dr. Prasad Kazibatla from Duke University, where he is professor of environmental chemistry in the Nicholas School of the Environment, and also has an appointment in the Pratt School of Engineering in Civil and Environmental Engineering. And Prasad's research focuses on developing a quantitative understanding of the factors that determine the chemical composition of the atmosphere using numerical models in conjunction with surface, airborne, and satellite-based measurements of atmospheric chemical composition. And as Prasad will describe, he has devoted some attention over the last several months to using his airborne and aerosol transmission modeling skills to look at indoor settings as well. So with that, let me welcome Dr. Jose Jimenez from University of Colorado at Boulder. And Jose, we look forward to your remarks. Thank you so much for joining us.
Okay, thank you very much. Next second, I think it's ready, okay. So hopefully you can see my slides. Okay, one second, yeah. So I'm gonna talk about the modes of transmission of SARS-CoV-2, what we know now, my take on what we know now, and I'll say a little bit about how to protect ourselves, though I won't have enough time to say a lot about that. But at the end of the talk, I will post my slides on my Twitter account, which is JLJ, so use my initials, Colorado. And if you go there, you can see the slides and you can follow all the links. So I will have links for all the references if you want to know more about something. Okay. So I'll start with what do we know about the modes of transmission? Okay. So the three modes of transmission for this disease are first surfaces. So we touch an infected surface or you touch someone else's hand, and then you touch the inside of your eyes, your nostrils, or your mouth, you can get infected. You can also get infected in two ways through the air, through these spray-borne droplets, or drops as they're called in this case, which are ballistic projectiles. They leave you when you talk or you cough or sneeze, and then they fly through the air like a bullet, and they can land on someone else's, again, the inside of the eyes, the inside of the nostrils, or the inside of the mouth, and that can lead to infection. And they're just made out of saliva and respiratory fluid. And at the same time that those droplets leave you when you talk or when you cough, there is many more aerosols, which are these dots of different colors, of different sizes. And the difference is that the aerosols don't follow a ballistic trajectory. They are too small. The drag of the air stops them. And then they float in the air for a period of, seconds, 2 minutes, 2 hours, depending on the size. And they infect by being inhaled. So we inhale them through the mouth or the nose, and then they can deposit in our respiratory system, and that's how they initiate infection. Everyone agrees these are the three routes to consider. There is disagreement, and the reason why we're having this part of the seminar is because there is disagreement on which one is more important. Okay? So I'll give my summary of the evidence. So I'll start to review evidence and say what it says about the routes. Okay? So the first thing is that we know, and I think this is not controversial at all, everyone agrees, the surfaces are not a major mode of transmission. The CDC tells us there's, for example, a famous hand washing study in the UK where people who wash their hands a lot had 16% less transmission for SARS-CoV-2 than people who wash their hands a lot less, right? And the debate I hear from the experts, I'm not a surface expert, but some people argue, well, maybe it's something like this, 10–20%. And other people argue in papers in the Lancet and other places that maybe it's 0 or 1% or something really small, right? So definitely surfaces are not how this pandemic is being propagated. And I won't say more about that in the rest of the talk. So then we're left with the two routes of droplets and aerosols. So we're going to review what different sources tell us about it. This is a paper that appeared in the journal Science, a letter in Science, the 5th of October, which I helped write with other people, but they only allowed so many authors. And what this says is that there is overwhelming evidence that inhalation means aerosols, is a major transmission route, okay? And that it is far more likely to inhale aerosols than to be sprayed by a droplet, okay? So it's telling us aerosols are important and aerosols are more important than droplets, okay? And this is not just the opinion of these authors, this is the summary of a workshop from the National Academies of Science, Engineering, and Medicine. There is 11 hours of recordings that you can watch, and then this was the consensus at the end of the workshop. So, so a lot of scientists think that aerosols are important. What do the CDC and the WHO tell us? So the CDC says it pretty confusingly, but they are telling us that aerosols are the main way the virus spreads. You have to know how to read their guidelines, okay? So if you go to their frequently asked questions, you see the sentence that says these particles, droplets or aerosols, whatever, can be inhaled into the nose, mouth, etc. And this is the main way the virus spreads. Okay? Inhalation is the main way the virus spreads. Only aerosols can be inhaled. And I'm going to show this. This is from the EPA webpage. So what can be inhaled? So this has been studied a lot for a number of reasons throughout the years. And what can be inhaled is something that has a certain amount in this curve that can be deposited in the respiratory system, and basically that starts at 100 microns. Something below needs to be smaller than 100 microns in order to be inhalable. Droplets, aerosols that are larger, they fall too quickly and they cannot be inhaled. Okay? So, and as we will see, the border between aerosols and droplets is 100 microns. So if it can be inhaled, it's an aerosol. And CDC tells us inhalation is the main way the virus spreads. It's telling us aerosols are the main way the virus spreads. They call them small droplets, and that has to do because they want to favor what's called droplet precautions in hospitals that actually work pretty well against aerosols. I think it's the wrong thing. I think they should explain that rather than create all this confusion, because then people in the community can't quite defend themselves against aerosol transmission because it's not being explained clearly. What about WHO? Well, it's even worse. At the beginning of the pandemic, there were mixed messages, but the 28th of March, they came out very clearly with this statement, which is still on their website, on their Twitter account, Facebook. that COVID is not airborne, is not in aerosols. This disease is not transmitted through aerosols. And actually, that saying so is misinformation. It's not just incorrect, it's misinformation to say it goes through the air. 2 days after this announcement went out, Lydia Moraska organized a group of scientists to contact WHO from many countries, from many disciplines, to tell them that this was wrong and that we thought there was evidence. And I became part of that group and basically have done a master's on airborne transmission with all the world experts by talking in this group. And we contacted WHO and we found a wall. We hit a wall. They were absolutely close to the idea that aerosols could play any role. So we ended up writing that letter with the 239 scientists, and a few days afterwards, they came out with this brief. This is the scientific brief from the 9th of July, which is still the latest one about transmission, and they say this large droplet transmission can occur. Okay? This can occur, and it will impact the mouth, the nose, and the eyes. About aerosols, they say, well, these physics have generated hypotheses, and this theory suggests, and a susceptible person could inhale aerosols. However, we don't know. And they later say, we need a lot of research. Everybody who reads this reads the message that these droplets we know that can occur, that's important. Aerosols, maybe, right? It has only been very recently, so this is really in the last 10 days, that high-level officials of the WHO, so Maria Van Kerkhove, Maria Negra, have given press conferences and recorded videos where they say that ventilation is very important to fight this disease. Okay? And Maria Negra went as far as saying we need 6 air changes per hour in a room, which is much higher than we normally have. Okay? But there's a problem. They didn't say why. So we need ventilation, but they don't say why. So they still talk about the droplets. And then we need ventilation. What happens? Ventilation only helps for aerosols. These projectiles, they don't care if there is ventilation. The surfaces, they don't care if there is ventilation. Aerosols are the only ones that care about ventilation, aerosol transmission. So they are telling us that aerosols are important because ventilation is apparently very important, but they are not telling us that aerosols are very important. So this is really confusing. And Christian Drosten, which is probably the most important advisor of Angela Merkel on this topic, who's a virologist, keeps saying the same thing I say. We have to explain how the virus is transmitted. If it's transmitted through aerosols, we have to say it. Okay? And there is a citizen petition, besides all the things the scientists have done, asking WHO to say it. It's called covidIsairborne.org. I haven't been involved, but I support their aims. If at the end of this talk you're convinced, go and sign it and pass the word around. Okay. So we're gonna review briefly some of the evidence about transmission. There is way too much evidence in favor of aerosols for me to review in the time I have. So what we know is that, as we said, surface is not major. We also know that this disease is easily transmitted in close proximity, like most respiratory diseases, right? And that social distance works. If you talk at a larger distance, then transmission is decreased. Okay. So what can we learn from that? WHO and people who kind of think on that framework, they tell us that basically the fact that the disease is easily transmitted in close proximity proves that it's droplet transmission. They make that conclusion. And they have a video on the webpage that say that for this disease where the droplets, these projectiles leave this person and very quickly they travel and they hit this person in the face and that infection ensues. And later in the video, they keep more of a distance, and then the droplets follow a parabolic trajectory, and they fall here, and then distance saves this person from being infected, right? This is a plausible hypothesis, but it's not the only one. It's not proof of droplets, right? This is actually a logical error that we pointed to WHO in April, and they have yet to accept. Okay. Because there is another alternative hypothesis, which is this is just due to the dilution of aerosols, right? And this is real, actually, imaging of the CO2 coming out of a person, and it has less contrast than this animation, but it's showing the same thing. Then, the aerosols come out, and eventually they're slowed, and then they rise, and distance helps in that way. This is so important, I'm gonna show you this video from Finnish researchers, and here you see how this person is talking, simulating talking, and then the air comes at a high speed first, But then it slows down, through friction. And here we will see a little more two people talking to each other. And you see again this high speed, but then it stops. And often because it's warm, it rises, and indoors is caught by the ceiling. And you can see if this person is keeping this distance versus if this person was here, he or she is going to inhale much different amounts of aerosols, right? So much like cigarette smoke, if you imagine if you were talking with a smoker and you were here or you were there, you would inhale, or you were there, you would inhale progressively less amounts of smoke. Smoke is just another aerosol, right? So basically, we have two ways of explaining why social distance works. And again, the smoke option and the observation that social distance work is not proof of droplets. That's one hypothesis. But now, if droplets are dominating the infection, then if you keep your distance, you can be indoors, you don't need a mask, you won't get infected because the droplets are going to fall within a couple of meters, right? Now, if the aerosols are the infection, you are not safe in an indoor space with low ventilation because, like smoke, they're going to accumulate in a poorly ventilated room, and even this person, which is far from the smoker here, can over time inhale enough smoke, enough virus to get infected, which is what we see in a lot of the super spreading events, right? So the evidence seems to actually point to the fact that social distance is evidence of aerosols and not of droplets. What else do we know about transmission? Well, we know that surfaces are not major. Sorry, I already said that. We know that indoors is larger than outdoors. That transmission is much easier. And I'll show one example. This is from contact tracing in Japan. So they followed the contacts of 22 cases and that were infected and met other people indoors, and 88 who met people outdoors. And the people who met others indoors, 16 of them got other people infected, 6 of them did not. Outdoors is completely reversed. 77 people didn't infect anyone, 11 infected someone. So we see already this is very lopsided. It's much easier to get people infected indoors than outdoors. And in terms of how many people got infected, we see that indoors you start to see numbers 3, 3, 4, 9, 12. You start to see super spreading, but basically only indoors. There is databases of super spreading events, and they are overwhelmingly dominated by things that happen indoors. And outdoors, you see a lot of ones. In one case, you see 2 or 3, and there are cases in which people were talking for a long time outdoors with a mask, and you can infect a few people, but not 52, like what we see in the choir. So now let's see the indoors and outdoors droplets and aerosols. Well, these ballistic projectiles, if you're talking to someone, they don't care, if you are indoor or outdoors. They have enough inertia to cross the air to receive the friction of the air and land in the eyes, the nostrils, or the mouth, right? And unless it's a really windy day, most days, basically the perturbation is small. So if droplets dominate the transmission, we should see something similar indoor and outdoors. Aerosols, on the other hand, they care a lot. The wind outdoors, even on a day that's not windy, is 10 times what it's indoors. And that wind is going to carry the aerosols, it's going to dilute them. We don't have a ceiling to trap them. So you would expect that if aerosols dominate the transmission, you will see much less transmission outdoors than indoors, which is what we see. Okay? What else? So the WHO tells us and their allies that this is a very different disease than airborne diseases, right? That have a much higher R number. And the accepted airborne diseases are measles, tuberculosis, and chickenpox, right? And this is more similar to what they call droplet diseases, incorrectly, in my opinion, but what they call droplet diseases, right? And, it has each person infects about 2.5 people or, some number around this. But it's a very variable disease. We know very well that this has a high dispersion. There is 10 to 20% of the infected that lead to about 80% of the new infections, these super spreading events. For those events, R is a very high number. And then there's many people who don't infect anybody. So we're gonna look at this evidence quickly. And for the super spreading, we're gonna use the example of the Skagit choir, which we investigated with colleagues. And when this happened, as soon as I read the article in the LA Times, I contacted the journalist who put me in touch with the choir, and the choir really bent over backwards to help us know every detail of what was going on. And I think it's the clearest case of the pandemic, in my opinion, because of the rigidity of the structure, I should say, of their actions. They got there. They were people who didn't have social contact otherwise. They were very focused on singing. They arrived just before the rehearsal. They sing. Then they have a 10-minute break where they have to go to the bathroom and do different things, and each person talks to 2 or 3 other people, and then they sing, and they leave pretty quickly. So basically the chances for the other routes of transmission to happen were very low, right? Just to say this picture is not from that choir, the density was about half this much because they knew about COVID and they were careful with surfaces and all that. So for the surfaces, we already learned that they are inefficient, and the person who was known to be sick didn't touch any objects. This person only went to a bathroom where 3 other people went. So, impossible to infect 52 people that way. Could it be the droplets? Well, there was no one 3 meters in front of this person, so any droplets that may have been coming out with singing, they were not landing in anyone. This person didn't talk to others, and others talked to 2 to 3 people during the 10-minute break. And CDC tells us that you need 15 minutes, of close contact to infect someone. So this is basically impossible, right? Could it be aerosols? It's very easy to explain, and kind of with a model similar to what Prasad will say later. We had low ventilation, a room that was well mixed, a long time, and no masks. So, it's easy to explain. And even quantitatively, when you apply the model, the amount of virus is about 10 times the amount in the famous restaurant and bus cases, which is consistent with singing very loudly. We know many more aerosols come out in that situation versus talking intermittently, like in the restaurant case. And what's most important is, this is just an example, all the super spreading events that have been investigated in detail, they all point towards aerosols. I think this one is the most undeniable, but they all point in that direction. And there isn't a single super spreading event I know of that has been studied and published or even submitted that points to surfaces or that points to large droplets. That doesn't exist. So super spreading is transmitting 80% of the disease, and super spreading is dominated by aerosols. Okay. But then we have this flip side that many people are not very contagious, and often it's said, people share the same home with someone infected and they don't know, and they don't get infected, right? And this is often used as proof that the disease is not transmitted through aerosols, right? But there is a logical error, another logical error here, which is that people who say this assume that someone who's infected is always putting a constant and high amount of aerosols in the air. So if the disease is airborne, anyone who shares the air with that person is going to get infected, right? Is this correct? Well, it's not, for several reasons, right? This is a graph of how infectious people are for this disease as a function of the symptom onset, and people are very infected for a short period just before the onset of symptoms, and as symptoms start, then as they get very sick and they can breathe and they go to the hospital, they are not very infectious, right? And here we see the droplet precautions work a lot of the time, and because you are dealing with people who are not very infectious. Yeah. And it's not just that. There is a study done by one of our colleagues in the group, Martian Zhao, and what they found, so they measured actually the virus coming out of people's breath, collecting it, and what they see is there is millions of virus per hour can be exhaled. But the most important finding, in my opinion, is they say this emission of virus is not continuous, it's sporadic. We don't know why, but some of the time viruses are coming out of people, and then the same person later, no viruses are coming out of them, right? So basically we have a disease that's variable, right? And so you get super spreading when you have the wrong time in the wrong location, has to be crowded, you have to be a long time, low ventilation, no masks, and vocalization of these things help. And probably you have super spreading people. It's known that some people emit many more aerosols than others for reasons that are not well understood. And also some people have much higher viral loads than others in the respiratory system. Okay? And you can have lack of transmission because, you have the people who have less aerosols or who emit less or who have lower viral loads, or use this sporadic emission as well as this shortness in time. So lack of transmission in a certain situation, a certain household, I think is evidence that there were not many infectious aerosols that time for that person, not for the whole disease. That's the logical error. Okay? And in fact, this fact of lack of transmission, despite sharing the air, was used for 75 years to tell us, public health authorities told us until about 1985 that measles, which now is used as the prototype scary airborne disease, we were told that it was a droplet fomite disease because there were famous cases in which people shared the air and others didn't get infected, right? So the same logical error that they made for 75 years, now they are making it again for COVID-19. So the last thing I will touch on, WHO will tell us, the droplets are larger, so they have many more viruses, and we can look at that, and they tell us, and this is still WHO's position, that the respiratory droplets are larger than 5 to 10 microns, and the aerosols are less than 5 microns. So these droplets that fall to the ground in a meter, in a second or two, in a few seconds, they are 5 to 10 microns. Let's check that, and we don't have to go very far. We just have to go to the CDC webpage where they have an aerosols 101 tutorial, and they tell us this is how much time they take to fall, right? So, 3 microns take 1.5 hours, 10 microns take 8 minutes. If you do the calculation, 5 microns take half an hour. So they don't take a few seconds, they take half an hour. So this is still WHO's position. And this is an enormous error. I mean, it's hard to emphasize just how huge of an error this is. It is 100 microns, as the science paper and as the national academies have told us. Things need to be 100 microns, which is by coincidence the border when things can be inhaled or not, to really fall on a few seconds, okay? So this is just a huge error. And Dr. Fauci, after Don Milton and Kim Prather from a group talked to him, he said, oh, yeah, of course. They have explained to us that this 5 micron thing was totally erroneous. And he's a smart guy. And he said, the bottom line is that there is much more aerosol than we thought. And the flip side of that is there are many fewer droplets than they thought, okay? And I'm gonna talk about that. So this is now, these lines are basically how many aerosols and droplets come out of people when they're talking, right? And there's different reasons I don't have time to explain. Just to know this is a log axis. So this is a 10 times, 10 times, 10 times, and this is another log axis. The virus is here, doesn't come out alone. It comes out in much larger vehicles of saliva, respiratory fluid. And, WHO was telling us, okay, these were aerosols and this is droplets. We have a ton of droplets, and they're bigger, they have more virus. But really, this is the correct border. These are aerosols, okay? And then you'll say, okay, so these are the droplets, there's still a few. But when you are talking, which I'm convinced is an important situation for spreading the pandemic, that's not correct. These basically are not droplets. There is a no man's land. These are not droplets nor aerosols because they are too small. They don't have enough inertia to reach someone. They need to be 300 microns, 4 times the diameter of a human hair, in order to reach someone. So now we're in a situation that we have a ton of aerosols, 1,000 times more aerosols than droplets, and very few droplets. And these very few droplets have to hit someone in the eyes, the nostrils, or the mouth in order to lead to infection. Okay, so this is really very, very unlikely, right? So the chances that infection proceeds through aerosols is much larger. And we can analyze that quantitatively. This is a model done by Hugo Lee in Hong Kong. This is the dose in microliters of saliva, respiratory fluid, that someone gets when talking to someone else, okay, through aerosols and through droplets, okay? And this is another log scale. This is a factor of 100, and this is a factor of 2,000, okay? So when you are talking a typical US conversational distance, you're inhaling a far larger volume of aerosols than you are being impacted by droplets, okay? Because of these physical reasons I just told you. And this is the volume of saliva respiratory fluid, but the volume doesn't contain, droplets and aerosols don't contain the same number of pathogens per unit volume. For all the diseases where this has been measured, the pathogens are concentrated on the aerosols disproportionately due to the reasons of generation in the respiratory tract, okay? So for all these diseases. So we're getting more dose by factors of 100 to 2,000, but there is probably another factor of 10, 100 or something that increases the aerosol dose, okay? So, it's no surprise that reviewing the literature on large droplet transmission, one can find no direct evidence for large droplets as a route of transmission for any disease. So we are told there is all these droplet diseases. Immediately COVID-19 was a droplet disease. Actually, there is no direct proof of that anywhere for any disease. For aerosols, there is, measles, chickenpox, tuberculosis, and actually there is a lot of evidence for the flu, SARS, MERS, rhinovirus. So, I mean, this is a total lopsided situation, and running short of time. So let me move quickly. There is some more information that you can find, but where I think we're going is that there is an error. I don't have time to explain the history. Maybe people have questions, I could, but basically there is an error that attributed this error that ease of infection in close proximity is due to droplets. It's an error that Charles Chapin made in 1910 at the same time that he discovered contact infection, and it has become a dogma, and it's a dogma that needs to fall. Okay? And in reality, I think most respiratory diseases, at least partially, all go through aerosols. And they all transmit best in close proximity because that's where aerosols are most concentrated. They can transmit in shared room air with low ventilation, the most contagious ones can transmit in another room or things like that, like measles. And we have a wide range of contagiousness. And this has huge implications, but this message is being resisted. This is someone in the WHO committee basically saying that we were unqualified to have an opinion about this, and that we maybe had economic interests. We maybe were owners of ventilation companies, right? And so there is this ignorant intruders like myself pushing this paradigm shift. But, you know, I think it's, we have to collaborate. And this is from a doctor in Twitter. And he said, you know, I feel like I'm getting a PhD in COVID and I need epidemiology, virology, immunology. There are many things, aerosol science. And I think this is about the right order. I don't think aerosol science is the most important discipline by far, but it is one where there's a huge error that we need to fix, and that's blocking controlling transmission of the pandemic. I think that's where we are. And so I'm out of time. So just very briefly, in terms of how to protect ourselves against infection, and then we can also discuss in the questions. We have put together this tinyurl.com/FAQ-aerosols. And basically every question I have seen that people had submitted is already addressed here in detail. And there's over 60 pages of details with links and references and whatever, and we can also discuss. The one thing I did want to mention is that we should measure carbon dioxide. That carbon dioxide with something like this that costs about $150 tells us how much exhaled air there is in a room and whether we are ventilating enough. So in this room, there is 1,100 parts per million. This means about 1.5% of the air that I'm breathing is air that I'm breathing for the second time. It's just mine, so I don't care. But if this was a classroom or an office, I'd be pretty concerned. And this number can go, I've seen number in classrooms now that people are measuring it that get to 5,000. That 10% of the air you're breathing has already been breathed in and exhaled by someone else. And that's really dangerous. So I think we should go to a situation, basically every space where we share air, there is a CO2 indicator with kind of a traffic light. This place is well or less well ventilated. And I'll leave it here since I think I already went a little bit too long.
Thank you very much, Jose. Yeah, you covered a lot of interesting material, and I know people have questions about that, but I want to be sure we get to Prasad's presentation as well, and then we'll take the questions and discussion after Prasad Kazibatla gives his talk. So thank you so much, Jose. And Prasad, please go ahead.
Thank you. So I'm going to pick up where Jose left off and talk about how we can use our understanding of aerosols to think about COVID-19 transmission risk quantitatively in indoor settings. So I'm going to start off by illustrating some basic aspects of airborne transmission in these settings, and then walk you through a relatively simple mathematical framework, I think, that can help us make some initial quantitative estimates of transmission risk. And then I'll show how we have implemented this risk estimation framework in the form of a web calculator, demonstrate its use for a specific classroom setting, and discuss some insights that it provides in terms of risk mitigation. And finally, close with some thoughts about next steps. So let me first start off with these illustrations that Lindsay Marr at Virginia Tech put together. This shows a room here, an infected person on the left, putting out aerosols. As you can see, there's a person close by who breathes this concentrated plume of aerosols that Jose talked about. There's also touching and large droplets indicated in the blue there. But as you get further away from the person, what the person's really inhaling is this background aerosol. And this is kind of the no intervention case. And then you can think of various interventions: source control, where the infected person is wearing a mask, cuts down on the amount of aerosols that the person is putting out, and the droplets as well. This is what we heard a lot about early on, about the mask being used to protect others. There's distancing so that you're not breathing in this concentrated plume, but also receptor masking, which would mean then that the CDC updated its guidelines this week to say that the masks also protect the people who are wearing them. And finally, ventilation and air filtration, as Jose pointed out, that can reduce the background aerosol. And you put that all together, and you can reduce risk substantially, and I'm going to talk about that. So let me walk you now through this mathematical framework in terms of how we think about this in terms of calculating risk. So here's the situation. Two people, there's some people indoors. There's an infected person here who's putting out virus as aerosols. There's a person here inhaling them, gets a certain dose, and depending on the dose, can get infected depending on a number of other parameters. Okay. Modulating this infected to infectious person transmission, there's a number of parameters. Room volume, obviously, it depends on how dispersed the virus is, the aerosol containing, the virus containing aerosols are. Duration of event is important because that determines the amount of total dose that you get. When these aerosols are emitted, they don't just stay there forever. They undergo a number of processes that we have to take into account to calculate risk quantitatively. Obviously, masks protect us in terms of cutting down a certain fraction of the aerosols that are emitted into the ambient atmosphere. There's mask inhalation efficiency because it protects us from breathing some of this aerosols in. As far as deposits, we can think about the rate at which this virus deposits. We quantify that in terms of this parameter K that I call Kdep here. There's also some evidence that the virus decays as depending on the environmental conditions in the room. So we have to take that into account. There's ventilation as you bring in fresh air and move the virus-laden air out, that you have to take into account the rate of ventilation. And finally, depending on your room, you might have some filtration as well, like an air purifier or something. So all of these parameters have to be taken into account to kind of quantitatively estimate risk. Now, for most of these parameters, we can either get some estimates of these parameters based on measurements, based on our understanding of aerosol physics. So we can kind of put some numbers on all these parameters. The difficult part, I think, in this exercise right now is understanding this virus emission rate, the extent to which people are putting out these aerosols laden with virus, and the dose-response relationship. Jose has already talked about the fact that different people put out this virus at different rates. Sometimes they put it out, sometimes they don't. So there's a lot of variability. There's variability person to person. There's variability depending on where you are in terms of where you are in the infectious period. And even in the infectious period, there's a lot of variability. So that's one of the challenges, I think, in terms of quantifying this risk. Okay. So we can address and get most of these parameters that we need, and I'm going to show you how we kind of put those together in the form of calculations that we can get at a probability of infection. But the tricky part is this virus emission rate and the dose response. So there's been some initial work done by some people here, by some people in various parts of the world. And what we do is we use this thing called the Quanta-based formulation. It's developed by Bonanno et al., also used by Jose and his group when they investigated the Skagit choir outbreak. And essentially what it is that you characterize virus emissions in terms of these units called Quanta, where the Quanta is defined as if you inhale one Quanta virus, you have a 66% chance of infection. You combine that with something called the Wells-Riley model, and you can calculate a probability of infection if you can calculate the amount of Quanta inhaled using this formula. So essentially, the problem now becomes calculating these Quanta emission rates, and then we can use our understanding of aerosol physics and understanding of the ventilation and air filtration characteristics of the room to calculate Quanta concentrations in the room. So what we have done here in our calculations is use these activity-dependent Quanta emission rates estimated by Bonanno et al. And essentially depends on the viral load in the sputum, which is variable, the expelled volume of respiratory aerosols, which is also variable, the infectious virusol virus per gene of gene copies of the virus, and another variable, which is pretty variable and uncertain. And these PFU stands for plaque forming units, the plaque forming unit based dose response relationship based on some other coronaviruses. This to me, this part of the calculations to me are the most uncertain in terms of what we know and what we don't know. So people have started to make first estimates of this. Again, it's pretty early on in the disease. And so these are uncertain, but we can still, I think, use these first estimates to get some first estimates of risk from a quantitative perspective. So let me just kind of show you some estimates here. So these are calculated distributions of these quanta emission rates. And remember, a quanta is if you breathe a quanta of this virus in, you have a 66% chance of getting sick. And these are estimates of quanta emission rates per person per hour, depending on whether they're speaking loudly, whether they're speaking or whether they're speaking loudly, based on these calculations and estimates developed by Buonanno et al. Okay. And you can see that there's a distribution here. The x-axis here is on a log scale. So this goes from about 0.01 quanta emissions per hour all the way to 10,000 quanta emissions per hour. Lots of variability, and depending on the activity, the louder you're talking, singing, the more you emit on average. And I'm going to talk a little bit about the significance of the spread in this log space in terms of this over dispersion that Jose talked about a little later in my talk. So I am going to, so you can take essentially what I showed here before, and now we're replacing this virus emission rate and the dose response in this combined parameter called the quanta emission rate, which essentially captures both those parts of it. And I'm going to use this framework then to figure out how to calculate risk and how to then implement it in this web-based framework. Okay. So once we have all of these parameters in here that determine these timescales of virus decay, timescales of ventilation, the efficiencies of mass and stuff, you can define an overall loss frequency that is made up of all these different loss frequencies. And based on that, you can calculate an average quanta concentration in the room, depending on the volume of the room and as well as the duration of the event. Once you do that, and you know the inhalation rate I here and the mask efficiency, you can calculate the quanta inhaled by the susceptible individual. And based on the Wells-Rayleigh equation, then you can calculate an infection probability. And this is precisely the formulation that we use in the web calculator that I'm going to show you in a minute. So I'm going to start by, I'm going to just take a minute or so to show you an example. And the calculation I'm going to use is my fall 2020 class. I started doing this because in the summer, we were asked to think about whether we're teaching in person or not. And I thought maybe I could do some calculations of my risk. It's a 16-person class. We meet 26 times during the semester, 75 minutes each class, each in-person session. The classroom is about 1,320 square feet. I talked to the engineers at Duke. The ventilation rate, which kind of combines fresh air ventilation and recirculated air filtered through a MERV 13 filter, we estimate that the combined ventilation and filtration air exchange rates are about 6 per hour. To calculate my risk in a classroom, I have to understand what is the chance that somebody who's infected in the classroom. For my calculations that I'll show you in a minute, I'm going to use the community infection percentage, which is the Duke community first-year students of 0.1 to 0.2%. This is based on Duke's COVID testing. Duke has been testing 15,000 or is conducting about 12 to 15,000 tests a week. And every week they're seeing numbers that are at most 0.1 to 0.2%. And we implement all of this in a web-based risk calculator. This was developed in collaboration with Jose, as well as my colleagues here, Bill Pan, Betsy Albright, and really I have to give a big shout out to John Fay. He's the one who first put this in the form of a web-based calculator that I think makes it easy to use. So I'm going to stop sharing my slides for a second, move to the web-based calculator, and then come back to my slides. So here's what our web-based calculator looks like. There's some preamble here, there's some instructions here, and there are parameters that you get to input and then calculate risk. Okay. So here, I'm one faculty member, 16 students, 26 class sessions, each of them 75 minutes. My classroom is about 1,320 square feet. It's about 10 feet ceilings. On the right side here are parameters that we don't know or are uncertain about, so you can give a range from a minimum to a maximum. The infection rate percentages, 0.1 to 0.2%. Conservatively, we estimate that mask prevent are about 40 to 60% efficient, both for exhalation and inhalation. My room ventilation rate is about 3 air changes per hour with about fresh air, and I estimate another 3 air changes per hour because of the MERV 13 filter. The virus, the decay of the virus infectivity, the rate at which it gets inactivated is pretty uncertain based on some people's estimates, based on some experimental data. We estimate that it's somewhere between 0 to 1 per hour is the frequency. The virus deposition rate depends on the size of the aerosols. Like Jose said, the size ranges from about 1 to 100 microns or so. So our deposition rate is about 0.3 to 1.5 per hour, the frequency. And then the inhalation rate is based on some EP estimates of typical rates of inhalation. These parameters here determine the Quanta emission rates based on the Bonan et al. Study that I kind of showed you. So you input all of this, you calculate the infection probability. What the model does is it calculates 10,000 combinations, taking 10,000 calculations with random combinations of these input parameters. That's called a Monte Carlo calculations. And what we output is we calculate our best estimate of infection probability. And in those 10,000 calculations, once we sort it out, we calculate the 5th percentile, the medians, the 95th percentile. So you can see that in this calculations for both the faculty and the student, the infection probabilities are pretty low. The infection probability for the students are slightly higher than the faculty because in this calculation, I assume the faculty is talking more loudly, emitting more virus particles. Okay? But you can see that in all these cases, the risk is very low, and this is for over the course of the semester. I'm going to stop sharing this, go back to my slides here. So just as an aside, when I did these calculations and I kind of developed, when we put out this web calculator, I was interviewed by a local TV channel and they asked me if I'm worried about teaching in person. And I said, no, based on my calculations, I'm not too worried about teaching in person. They took out the teaching in person part and the news got out that I was not worried about the calculation, about the virus at all. My friend made me a coffee mug that kind of says that, so I have to live with the shame for the rest of my life. Okay, I'm going to show a couple of other calculations. This is a slightly different calculation using the same web calculator. And what I'm looking at here is what happens if there is an infected person in the classroom. And the way I do that is by essentially setting the community infection percentage for the faculty member to 100%. And that then ensures that there's an infected person in that model classroom, and I can look to see what happens. So I look over the course of a week, and I look at a base case where there are 2 75-minute in-person sessions. There's only ventilation, there's no air filtration and no masks. And I look at four other cases, one in which the only thing that's changed is instead of 2 75-minute in-person sessions, we have 3 50-minute in-person sessions. The next case is the same as the base, except you add air filtration. The masking is the same as the base, except everyone's wearing masks. And the last case is all of these. And what I show here is the results of 20,000 Monte Carlo runs for each case. If you're familiar with this, these are called violin plots. The colored area represents the distribution of results for the infection probability here. The top line here in each of these violins shows the 95th percentile from these 20,000 Monte Carlo runs. And the lower bar here shows the means for each of the runs. You can see that if you just look at the means, the risk here was about 4.5% for the base case. Changing the duration just changes just a little bit, not too much. Air filtration does quite a bit. It's not really proportional. Part of the reason it's not proportional is because there's also the deposition term that doesn't change. And also there's a transient effect that gives some slight nonlinearity. Masking makes a big difference. And by doing all of these, you cut down your risk significantly. We kind of know this, but this is putting some numbers on it. The final thing I'll say is if you look at these calculations, you can also kind of sort out those 20,000 calculations in terms of this, how many people are infecting how many people. And if you plot it in this infected number of infectors on the x-axis here and number of infected, what we find is that 75% of the people here only contribute to 20% of the infections, and the remaining 25% contribute to 80% of the infections. And so this kind of relates to this over-dispersion issue. This airborne transmission mechanism, at least qualitatively and even semi-quantitatively, seems to be consistent with this this pattern of over-dispersion. Okay. Now, obviously, this is a very idealized case. This is not really in the real world. People are interacting in a whole number of different ways, and you really have to take that into account to really make the case that there is a consistency. But I just want to point out that this, at least qualitatively, we seem to be able to get that. And this is largely because of the fact that the emissions are distributed log normally. So most people are emitting kind of in the low range, while a few people are emitting in the high range. So finally, some parting thoughts. Again, I will point you to this airborne transmission workshop. A number of those, all the recordings of that workshop are online. There's a workshop summary. And as Jose said, his FAQ that he has led putting together is excellent. I have one thought about a way forward. As you know, there's a number of models that have been developed, these epidemiological models to predict large scale spread. There was an article in Nature this week, an excellent article by a group at Stanford and other places, where what they did was they looked at mobility networks. They looked at some 95 million people on an hourly basis using cell phone data for mobility, along with some data on locations they were at, what they call places of interest. They overlaid that with an SEIR model to calculate what exactly was driving the epidemic and what control measures could do about it. What I think would be really interesting to do is to couple the kind of mechanistic models we have for individual events based on these aerosols to these type of large-scale models to see if these aerosol transmission can explain the large-scale dynamics. I think it's going to be challenging, but I think it's going to be very interesting to try to do this. So if there are people in the audience who are working on these SEIR models and are interested in this kind of stuff, I would be very happy to hear from them. So I'll stop here, Jonathan, and I guess you'll moderate the questions.
Right. Thank you, Prasad. Really, really interesting. And if nothing else, you showed the complexity of trying to develop these quantitative estimates with so many different variables and the uncertainties. We have between just over 15, almost 20 minutes for Q&A because we conclude at 12:15. And there have been numerous questions that were submitted in advance. And also there's been a lively set of questions in the Q&A box on Zoom today. And I see Jose has already been answering many of those questions. So I wonder if I could just collect several questions that seem to be grouped on the same topic and ask you, Jose, to repeat a little bit of what you have said in writing, but very briefly. And then I have a similar grouped set of questions for Prasad. And then I may be able to call on some individuals, but I wanted to group some of these questions which several people had posed so that we are sure to get to them. So, Jose, several people have asked about CO2, carbon dioxide levels as a proxy for, I guess, for exhalation indoors, and therefore as a proxy for the continued exposure to what people have exhaled, the virus that people have exhaled indoors as compared to outdoors, or should we, how reliable are the CO2 levels as a proxy for virus exposure, or should we have some kind of limits or regulatory standards set for CO2 levels in indoor settings? And I noticed that question from, and I hope I'm pronouncing these names correctly, but from Ross Salowich and Mo Ing and Olav Vaitinen and Angie Gomez, and probably from some others. There were also a couple of questions about humidity levels or dehydration of the droplets, and from Hannes Fischer and perhaps others. So Jose, could you comment quickly on CO2 and humidity?
Yes. So we think CO2 is extremely useful, and this was actually news to me. I didn't know these monitors existed. They're actually very accurate against research monitors, and they're affordable, right? $150, every school should have one, and then monitor all the classrooms and every business. It is the one thing that we can measure that has a very good signal to noise, is a very clear evidence. It's mostly influenced by our exhaled air. So, and a lot of people are measuring, and we have this tag in Twitter, COVID CO2, and it's pretty clear, right? And what people are finding is in many classrooms, you have easily 2,000, 3,000, 5,000 parts per million, these levels where you're rebreathing a lot of exhaled air. And we know that if there is virus there, that's dangerous, right? And then we are proposing levels which are, 700 is what I've been saying. And, is 700 an absolute number? We actually written a paper on that. It's kind of like 1 meter or 2 meters. You have to say something that's reasonably feasible. Less than 700 would be better. But what's important is to come down from 3,000 to 700. Some people try to say, well, could we measure the respiratory aerosols themselves? The problem is those are very few, and they're very hard to tell with the background of aerosols from many other sources. So that's a researchy question, but is much less practical for the average person. And for humidity, it is known that these envelope viruses and SARS-CoV-2 has already been shown, it has a U shape. It survives very well under dry conditions and under very humid conditions. And 40 to 60% humidity, it seems to decay faster. And there is a paper submitted that says they think that's because the aerosols still have water, but the salts and everything is very concentrated, and the chemical reactions that deactivate the aerosol go faster, between 40 and 60%. And there is some people who favor humidity control, that we should invest in humidity control as a way to control the pandemic. And what they're saying is, the virus is going to be in the air, let's shorten its lifetime. Let's make it decay faster. What I say is that humidity control is not easy. It costs money. You have to have systems. Why don't we instead ventilate or have filters that remove the virus from the air? I'd rather remove it than leave it there and shorten its lifetime.
Okay, thank you. Thank you very much, Jose. The last comment you made about ventilation is a good segue to the set of questions I wanted to ask Prasad, because in your models, when you're looking at ventilation rate, that seems like an important variable. You tell me if this is correct. That might be a variable that each building manager could be able to influence the ventilation rate. I don't know how costly it is to change the ventilation. This is also a question that's come up not only about indoor building air in many settings, in restaurants, in classrooms, but also in airplanes. And there were questions about classrooms from David Shanzer and Susan Dunlap, and about airplane flights from Zize Kui, and about theaters from Robin Pooley, and about there may be others who have posed these questions. Oh, and then there was a question about from Vimal Baya about whether opening windows, can you put in your model how many windows are open or not, or how does that affect the ventilation rate? So could you comment, Prasad, a little bit more about the ventilation or air exchange rate of the indoor space?
Right. So let me just say, did you say Susan Dunlap by any chance? Because she's my wife and I'm surprised
I did. Yes, I did.
She's submitting questions to me online. So
She has asked about clean. She actually asked about what difference does it make to clean the classrooms?
okay. So so let me talk about ventilation. So ventilation clearly is key, but when we talk about ventilation, we're typically talking about bringing in outside fresh air. So anything that we can do to do that helps. Some places have windows which you can open. You can significantly improve ventilation rates. Within typical types of buildings, my understanding is that it's hard to do. You can probably do that to some extent, and you should do that to the extent you can. But I think there's this other side of the story, which is just as important, which is air purification. Jose talked about it a little bit. That is critical, and you can often do that either through the HVAC system by upgrading the types of filters you're using, or by using portable air purifiers with appropriate clean air delivery rates. So, those are all extremely important, trying to understand this. In terms of understanding fresh air ventilation, as Jose has kind of touched on, you can actually use cheap CO2 monitors. You can actually do some pretty simple experiments in the rooms to kind of get at what your fresh air ventilation rate is and how that might change if you open windows and stuff. And again, the conventional wisdom seems to be if you can get up to 4 to 6 air changes per hour, that is pretty good. Jose, I don't know if you want to comment more on that.
Yeah. I mean, I think I've been working a lot with people who are measuring CO2 in classrooms, especially. There is a lot of interest. I'm going to share my screen for a moment. This is data from my hometown in Spain. Hopefully you can see from a classroom, and this is the CO2 level. And this is 2 different days following the same schedule where the windows are open. If the windows were not open, they were getting to 2000. And in this case, they have 3 windows open 7.5 centimeters. And in this case, 3 windows open 15 centimeters. So they're not fully open, and they're not all the windows that are open. And what you see is very quickly, you have people arrive, the kids arrive, and you have a transition to a steady state. And then more or less you have a relatively constant level. Then they leave for the outdoors, and then it goes down. And then they come back, and again, you reach a new steady state. And here they change the ventilation, they open 1 more window, and then the level goes down. So basically what you see in these places that have windows is that relatively quickly you reach a relatively constant level if everything else stays similar and the wind stays the same. But it depends a lot on the classroom, what kind of windows they have, and what's the wind in that place, whatever. So, but this is what we were advocating, is if a school can get one CO2 monitor and do this in every classroom as a project for the students, there are many places where this is feasible. Now, we are also being told that there are places where this is not feasible. They don't have enough windows, or the windows cannot be open, or things like that. And then you need to do other things. But in many modern commercial buildings, again, the windows cannot be open, so then you can't. But a lot of schools are old buildings where you can do this kind of thing.
But again, I would just again stress there's the air purification part of that also, and that can also buy you just as much as ventilation can. And you can often do that even in places where you can't open windows and stuff.
And if I may, if I may add one thing, is like these air purifiers are expensive, and people say, oh, this costs $400. We're gonna instead ventilate by opening the windows. But in many places where the winter is cold, you may spend more than $400 in extra heating costs. So you have to, I don't know if people have done these calculations, but you have to think about both approaches.
Yeah, okay, and good point. And I'm glad you showed, Jose, the slide about the different window openings and opening window. I should have mentioned that Sean McHugh also posed that question about opening the window and airflow. One question I always have about that is that just an issue for the building managers to try to ventilate more, or is there any way for individuals, for members of the public, to find out what the ventilation rate is in a building before going into that building? If it varies significantly across different buildings or different indoor spaces, should that be posted on the exterior of the doorway, or how would we find out that information?
So if I can if I could just address that briefly. So Tammy Bond, who's at Colorado State, has proposed this metric called effective rebreathe volume, which kind of gives you a sense of the extent to which there's ventilation for different particle sizes, and that be posted on all these buildings. Now, I think that's still a ways away, but I think what people in the atmospheric science community are advocating is what Jose talked about, which is at the very least, all these rooms have CO2 monitors that you kind of take a threshold. You can pick 800, you can pick 750, 700, something in that range. And that's about as well as you can probably do in terms of ventilation in many of these spaces. And so that's what you should target. And if there's something, if it goes above that, then there's something really you need to work on.
Okay, let me try to invite, if we can, with the time we have left, a couple of people who have posed questions to pose those questions orally. I noticed that, for example, Peg Coleman posted a couple of questions in advance and in person today about asymptomatic people exhaling and how that affects the viral load and perhaps another. So Peg, if you can, please go ahead.
Can you hear me, Jonathan?
Yes.
My concern is that the US and so many other countries are not even measuring the quantitative load when they're analyzing samples. It's reported as positive, negative. And it seems counterproductive when these tests can give us quantitative numbers. And what are your thinking about how generating more quantitative data, especially for asymptomatic people, might there be benefits to managing or controlling the pandemic by doing more quantitative testing?
Well, I mean, there are researchers who are proposing exactly that people have very different viral loads. They vary by enormous amounts. And either with the PCR test or even with the antigen test, which basically detect the people with the higher viral loads, that we should use that information. And people with the higher viral loads should be quarantined longer, and people with low viral loads should maybe they need to isolate for as long. So I agree that that will be a smart way to manage the pandemic. Yeah.
Yeah, and I think it also comes down to this issue that there's this over dispersion, which means that a few people are infecting many people, and those few people are probably those with those high viral loads. And so to the extent that you can quickly trace and isolate that and bust these clusters, in my mind, that's what's kind of critical in terms of managing the pandemic.
Thank you.
Okay, now let me see if Dana Krug or Maya Kofschultz are with us right now, because they both posed questions about what should we be thinking about as the winter arrives and the weather gets colder and people are indoors more, including not only for classes and eating, but also for sports. So I see Dana there. Please go ahead.
Hi, this is Dana Krug. I'm wondering what the risk assessment, what do you think is the risk assessment for running like indoor sports like basketball, wrestling, track among a younger population like high school students? I'm a school board member in a community that's dealing with this issue right now, and we're trying to figure out a safe way to do this if possible, but with the numbers and the rates going up, I'm wondering what the risk assessment would be. Thank you.
Jose, do you want to do the gym stuff?
Okay. I mean, I think we can both answer, or maybe we can both give us our take. I mean, these are risky situations, and we see the study from Nature that Prasad mentioned found gyms were a hotspot of transmission, which is consistent with aerobic exercise. And there was a case in Korea where aerobic gym exercise led to transmission, and when the same infected person was there, but they were doing yoga and without aerobic exercise, then there was no transmission. So we know that people who are breathing hard are putting more virus in the air and they are inhaling more virus. So, I mean, so doing it with masks, even though it's a pain, but maybe if everyone wears the same mask, everyone is penalized in the same way. doing it outdoors whenever possible would be safer. I mean, these rooms have a lot of volume, much more than a gym, so that helps you to dilute the virus. But I would say it's medium risk situation. I don't know, Prasad, what do you think?
Yeah, I think it's medium risk too, but I think the other aspect here, which there's this other variable, which is time. And I think to the extent to which you can do this for limited periods of time, as opposed to a long, lengthy, maybe if it's 20 minutes, half an hour. I mean, anything you can do reduces risk. It doesn't really eliminate risk. So the extent to which you can maybe, limit the number of people, masks, limit the amount of time each session, I think that goes a long way. And of course, the other big variable is the community risks, community infection percentages. We talk about school opening, we talk about high school sports and stuff, but I think to do that in a relatively safe fashion, we have to drive down community infection risk. So there's kind of has to be that trade-off, because that in turn determines to what extent what people are, somebody infected in the community, then bringing it into these specific situations, that increases the risk.
I know we've had a number of other questions in the Q&A, and some of them Jose and perhaps Prasad have already answered, so we really appreciate that. Several of the questions asked about whether links to slides or links to the brand name of the CO2 monitor or other information could be provided, and so perhaps we can provide that in the chat box as well.
I did post my slides, and that's already on the chat, and I will post the name of the CO2 monitor now. I just did.
Great, thank you. So
Jonathan, I can send you my slides, and I'm assuming there's a recording of the event that you'll
yes,
have.
we are recording the event, and I believe Tyler Felgenhauer has already answered on the Q&A that he's going to post the recording.
And will the chat Q&A be saved so that we can answer after the fact?
That may be possible if.
Yeah, we'll have all information, links, slides, the recording, and the chat Q&A available, and we'll send that out.
And I'll just say if people want to email us directly with their questions, we'll be happy to answer.
That's great, thank you. So I wonder if we're just at the very end now at 12:15. There was also a question from Martin DeCock, who I see is on the line, but if you'll forgive me, I'll just pose the question quickly, which is, why do you think, Jose and Prasad, that the WHO has been, seems to have been reluctant to acknowledge the aerosol airborne transmission pathway?
This is up Jose.
I've talked with them a lot, and there's basically two reasons. There is a historical reason, as I mentioned briefly. In 1910, Charles Chapin, who was then the president of the American Public Health Association, writes a book where he basically establishes contact infection, which is the concept that we get germs from other people. Right? We get sick, we get COVID or tuberculosis because someone gave us the germ, not the germ wasn't living out there in putrid water, right? So that's a huge advance. But at the same time, he says that airborne transmission is almost impossible. And the whole package has become the dogma of infectious diseases and epidemiology until now. And it's really only this pandemic that's uncovered that this is a huge error. But for the WHO types, this is unthinkable. I mean, when we talk to them, it's like they had resurrected Chapin, and he was talking to us and I was saying, but this is so unlikely, and you need this huge level of evidence. And we told them, but you don't have that evidence for droplets. And yeah, but we know droplets happen. We know that, because it's a tradition. The other aspect is practical, and it has to do with this thing about the droplet precautions and the airborne precautions and the scarcity. But what we've been telling them is, by not telling people how to protect themselves, more people get sick, and then more people go to the hospital, and you need more masks, and the masks continue to be scarce. So anyway, that's in briefly what I think is going on.
Prasad, did you want to comment?
No, I think this is not a community I've engaged with. Jose has been really leading the charge on that. Jose and Lindsay Marr and Kim Prather, they've been the ones leading the charge.
And as you noted, there's been a large number of epidemiologists and microbial risk assessors and others who have written to WHO and others to point out the importance of aerosols and the literature that you cited. So thank you so much Jose Jimenez and Prasad Kazibatla for a fascinating discussion that raised many additional questions. And thank you everyone for participating. We really appreciate your attention and your questions. And thank you for letting me group and pose several of the questions. So thank you all. We look forward to seeing you at the next of our Duke Center on Risk webinars. Thank you.
Thank you.
Thanks, Jose.